Good morning. Happy Monday morning. It's gonna be time for another Rust book stream. All right, our preview is working. Sound seems to be going out. Let's go. Stream health is good. Let's go set up where we are. It looks like we're currently at advanced traits. That is chapter 19, so I can also update. I can also get a code opened in that area too, and then we'll be getting started around 7 o'clock. All right, so CD Dynamically projects, in Rust, chapter 19. Oh, so the last thing we actually had code to write was safe Rust. We are on third subsection, advanced traits. So we may or may not need. That's fine. And everything else seems to be pretty good. Can't remember. I don't think we even read this section, like this a little bit. All right, so I'm just gonna go ahead and get started here. Advanced traits. We first covered traits in a traits defining shared behavior section of chapter 10, but as with lifetimes, we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty-gritty. Specifying placeholder types and trait definitions with associated types. Associated types connect a large placeholder with a trait such that the trait method definitions can use these placeholder types in their signatures. The implementer of a trait will specify the concrete type to be used in this type's place for the particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We've described most of the advanced features in this chapter as being rarely needed. Associated types are somewhere in the middle. They're used more rarely than features explained in the rest of the book, but more commonly than many of the other features discussed in this chapter. One example of a trait with an associated type is the iterator trait that the standard library provides. The associated type is named item and stands in for the type of the values the type implementing the iterator trait is iterating over. In the iterator trait and the next method section of chapter 13, we mentioned that the definition of the iterator trait is as shown in listing 1920. So public trait iterator type item. Okay, so this is what they're talking right here. Function next, self, option, self item. The type item is a placeholder type, and the next method's definition shows that it will return values of type option self item. Implementers of the iterator trait will specify the concrete type for item, and the next method will return an option containing a value of that concrete type. And associated types might seem like a similar concept to generics, in that the latter allows us to define a function without specifying what types it can handle. So why use associated types? Let's examine the difference between two concepts with an example from chapter 13 that implements the iterator trait on the counter struct. In listing 1321, we specified that the item type was U32. All right, so implement iterator for counter item u32 function next. I mean, I get okay, so type item equals, whereas this is just type item. We're just saying it has to be u32. This syntax seems comparable to that of generics, so why not just define the iterator trait with generics as shown in listing 1921? The public trait iterator t function next mute self option t. The difference is that when using generics, as in listing 1921, we must annotate the types in each implementation because we can also implement iterator string for counter or any other type that we could have multiple implementations of iterator for counter. In other words, when a trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic type parameters each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associated types, we don't need to annotate types because we can't implement a trait on a type multiple times. In listing 1920, with a definition that it uses associated types, we can only choose what the type of item will be once, because there can only be one implement iterator for counter. We don't have to specify that we want an iterator of u32 values everywhere that we call next on counter. That's the problem with generics, because it would make it so that we could, well, so we'd have a function like if we have the implement trait that's generic, then it could be like u32, i32, u64, i64, u8, i8, like basically everything, every single possible thing, including strings, everything else would be possible now. And we know we want more control over that. Default generic type parameters and operator overloading. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type if the default type works. The syntax for specifying a default type for a generic type is, so placeholder type equals concrete type when declaring the generic type, which is sort of what we saw with here. This is a placeholder type equals concrete type. A great example of a situation where this technique is useful is with operator overloading. Operator overloading is customizing the behavior of an operator, such as plus, in the particular situations. Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations and corresponding traits listed in standard ops by implementing the traits associated with the operator. For example, in listing 1922, we overload the plus operator to add 2 point instances together. We do this by implementing the add trait on a point struct. So we bring in the add trait, so standard ops add. Okay. We have our struct point, implement add for point. Type output equals point. Function add, so self other is a type point, returns a type point, and then we're just going to return the struct point with self plus other.x. Interesting, okay. To add 2 point, okay, yeah. I mean, so this is just adding two, like adding two vectors together. The add method adds the x values of the 2 point instances and the y values of 2 point instances to create a new point. The add trait has an associated type named output that determines the type returned from the add method. So it's because we've added the add trait, we can now do things like this. is just say like, hey, take a point and add a point to it. And because we have the plus sign here, allows us to say like, well, hey, add is the trait. And so therefore our output is going to be a point, and now like run this function whenever we call this. The add trait has an associated type named output that determines the type returned from the add method. The default generic type in its code is within the add trait. Here's its definition. So trait add, RHS equals self. I don't know what that is. Type output function add. All right. This code should look generally familiar. A trait with one method and an associated type. The new part is RHS equals self. This syntax is called default type parameters. The RHS generic type parameter, short for right-hand side, defines the type of the right-hand side parameter in the add method. If we don't specify a concrete type for RHS, when we implement the add trait, the type of RHS will default to self, which will be the type we're implementing add on. So, well, I guess that's a trait. I wonder if that works in functions too. When we implemented add for point, we used the default for RHS because we wanted to add 2 point instances. Let's look at an example of implementing the add trait where we want to customize the RHS type rather than using the default. That was annoying. Phone is too loud. Yeah, that should be better. We have two structs, millimeters and meters, holding values in different units. We want to add values in millimeters to values in meters and have the implementation of add do the conversion correctly. We can implement add for millimeters with meters as the RHS, as shown in listing 1923. So we bring in add. So we have struct millimeters, which is U32, struct meters, U32. Implement add meters for, so is this struct right here, 4 millimeters. Type output equals millimeters, function add, other. Okay, so basically it's just the type is, we're implementing add for this type, meters. And I wonder, like, can we also say like implement add millimeters for millimeters, and then the opposite for everybody else? To add millimeters and meters, we specify implement add meters to set the value of the RHS type parameter instead of using the default of self. You'll use default type parameters in 2 main ways: to extend a type without breaking existing code, to allow customization in specific cases most users won't need. The standard library's add trait is an example of the second purpose. Usually, you'll add 2 like types, but the add trait provides the ability to customize beyond that. Using a default type parameter in the add trait definition means you don't have to specify the extra parameter most of the time. In other words, a bit of implementation boilerplate isn't needed, making it easier to use the trait. The first purpose is similar to the second, but in reverse. If you want to add a type parameter to an existing trait, you can give it a default to allow extension of the functionality of the trait without breaking the existing implementation code. So it sounds like we wouldn't need to have like an add, like add millimeters, 4 millimeters, because this is just a number. Now, if this wasn't a number struct, then we probably would need to implement those ourselves because we wouldn't know how to add anyways. Fully qualified syntax for disambiguation. Calling methods with the same name. Nothing in Rust prevents a trait from having a method with the same name as another trait's method, nor does Rust prevent you from implementing both traits on one type. It's also possible to implement a method directly on the type with the same name as methods from traits. When calling methods with the same name, you'll need to tell Rust which one you want to use. Consider the code in listing 1924, where we've defined two traits, pilot and wizard, that both have a method named fly. We then implement both traits on a type human that already has a method named fly implemented on it. Each fly method does something different. Okay, so we have trait pilot that has function fly, trait wizard that has function fly, struct human, it's defined, it's empty struct, implement pilot for human. So the function fly here is this is your captain speaking. Okay, so this is basically adding in, okay, so implement pilot for human and then adding in fly. Implement wizard for human, so now the human is a pilot and a wizard, and both can fly, so print line up. Implement human, so just normal implement human, and it has its own fly, which, okay, so there's three fly functions, just to make it maximally confusing. When we call fly on an instance of human, the compiler defaults to calling the method that is directly implemented on the type, as shown in listing 1925. So this one. Running this code will print waving arms furiously, showing that Rust called the fly method implemented on human directly. To call the fly methods from either the pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. Listing 1926 demonstrates this syntax. So that person equals human, pilot, fly. So we need to then use the trait. So like using the trait directly, call that function and hand it a reference to the person, and it'll then like call it. Specifying the trait name before the method name clarifies to Rust which implementation of fly we want to call. We could also write human fly reference to person, which is the equivalent to the person.fly that we used in listing 1926. But this is a bit longer to write if we don't need to disambiguate. Running this code prints the following. So, yep, sort of like what we would expect, 3 different flies in order. Because the fly method takes a self parameter, if we had 2 types that both implement one trait, Rust could figure out which implementation of a trait to use based on the type of self. However, associated functions that are part of traits that don't have a self parameter, when 2 types in the same scope implement that trait, Rust can't figure out which type you mean unless you use fully qualified syntax. For example, the animal trait in listing 1927 has the associated function baby name. The implementation of animal for the struct dog and the associated function baby name defined on dog directly. Okay, so we have trait animal, which is a function name which returns a string, struct dog, implement, so standard implement on dog, function baby name, string from, okay, so this just returns the string spot. Implement animal for dog, function baby name, string, so this returns puppy. Okay. Function main, a baby dog is called, and then dog, baby name. Interesting. So we didn't it looks like we didn't like instantiate a new instance of dog. We're just calling it based upon the struct itself. This code is for an animal shelter that wants to name all puppies Spot, which is implemented in the baby name associated function that is defined on dog. The dog name type is also implements the trait animal, which describes characteristics that all animals have. Baby dogs are called puppies, and that is expressed in the implementation of the animal trait on dog in the baby name function associated with the animal trait. In main, we call the dog baby name function, which calls the associated function defined on dog directly. This code prints the following. Baby dog is called Spot, a Spot. This function isn't what we wanted. We want to call the baby name function that is part of the animal trait we implemented on dog. The code prints a baby dog is called a puppy. The technique of specifying the trait name that we used in listing 1926 doesn't help here. If we change main to the code listed in 1928, we'll get a compilation error. Okay, so animal baby name, that's sort of what I figured to do, but that won't work, apparently. Because animal baby name is an associated function rather than a method, and thus doesn't have a self-parameter, Rust can't figure out which implementation of animal baby name we want. We'll get this compilation error. Type annotations required, cannot resolve. To disambiguate and tell Rust that we want to use the implementation of animal for dog, we need to use fully qualified syntax. Listing 1929 demonstrates how to use fully qualified syntax. So a baby dog is called, so dog as animal, baby name. Oh God, that's terrible. We're providing Rust with a type annotation within the angle brackets, which indicates we want to call the baby name method from the animal trait as implemented on dog by saying that we want to treat the dog type as an animal for this function call. This code will now print what we want. A baby dog is called a puppy. In general, fully qualified syntax is defined as follows. Type as trait, function, receiver if method, next arg. For associated functions, there would not be a receiver. There would only be the list of other arguments. You could use fully qualified syntax everywhere that you call functions or methods. However, you're allowed to omit any part of the syntax that Rust can figure out from other information in a program. You only need to use this more verbose syntax in cases where there are multiple implementations that use the same name, and Rust needs to help to identify which implementation you want to call. So I mean, the thing, like the takeaway that I'm getting is it's more important to know that this is possible than to memorize like how to do this, because sometime far down the line, I'm going to run into this problem, and at that point in time, I need to know that I can go and look it up. Using super traits to require one trait's functionality within another trait. Sometimes you might need one trait to use another trait's functionality. In this case, you need to rely on the dependence trait also being implemented. The trait you rely on is a super trait of the trait you're implementing. For example, let's say we want to make an outline print trait with an outline print method that will print a value framed in asterisks. That is, given a point struct that implements display to result in x and y, so a tuple x and y, when we call outline print on a point instance that has 1 for x and 3 for y, it should print the following. So the asterisk and then the 1 and 3. In the implementation of outline print, we want to use the display traits functionality. Therefore, we need to specify that the outline print trait will work only for types that also implement display and provide the functionality that outline print needs. We can do that in the trait definition by specifying outline print display. So basically saying the type of outline print is display. I mean, that's sort of like what the syntax looks like. This technique is similar to adding a trait bound to a trait. Listing 1930 shows an implementation of the outline print trait. So use standard format, trait outline print, format display, function, trait outline print, colon, format, display. So we're saying that outline print requires display. Then we have function outline print, and we just do all the things. Because we specified the outline print requires the display trait, we can use the TwoString function that is automatically implemented for any type that implements display. If we tried to use the TwoString without adding a colon and specifying the display trait after the trait name, we get an error saying that no method named TwoString was found for the type self in the current scope. Let's see what happens when you try to implement outline print on a type that doesn't implement display, such as the point struct. We get an error saying that display is required but not implemented. So the point-centered format display is not satisfied. To fix this, we implement display on point and satisfy the constraint that outline print requires. So implement format display for point, but then we have to actually write that code. Then implementing the outline print trait on point will compile successfully, and we can call outline print on a point instance to display it within an outline of asterisks. Using the new type pattern to implement external traits on external types. In chapter 10, in the implementing a trait on type section, we mentioned the orphan rule that states were allowed. This feels like it shouldn't be an apostrophe there. Just states were allowed. I kind of feel that I want to put that in here. Let's see, I know that we have a documentation fixes for books. Okay, so we have chapter 14. Chapter 19. And specifically, go all the way to here, get this sentence. And then we can say, that should just be where. All right, so that should be good there. In chapter 10, in the implementing a trait on type section, we mentioned the orphan rule that states were allowed to implement a trait on the type as long as either the trait or the type are local to our crate. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple struct. We covered tuple structs in the Using Tuple Structs Without Named Fields to Create Different Types section of Chapter 5. The tuple struct will have one field and be a thin wrapper around the type we want to implement a trait for. Then the wrapper type is local to our crate. We can implement the trait on the wrapper. New type is a term that originates from the Haskell programming language. There is no runtime performance penalty for using this pattern, and the wrapper type is deleted at compile time, so like joined together at compile time. As an example, let's say we want to implement display on vec_t, which the orphan rule prevents us from doing directly because the display trait and the vec_t type are defined outside our crate. We can make a wrapper struct that holds an instance of vec_t. Then we can implement display on wrapper and use the vec_t value as shown in listing 1931. So use standard format, struct wrapper. So it looks like a wrapper is going to be a tuple struct that has a vector string. Implement format display for wrapper. Function format. Interesting, I would have expected it to be display. So function format takes in a reference to self, takes in f, which is a mutable formatter, a mutable reference to formatter, and returns a format result. And then we just write out f, whatever f is. Also, looks like an array, almost like a vector of objects, of like structs. Self.0.join. Interesting. So function main, let w equals wrapper, vec string from hello, string from world. So that's a vector of two things. Print line w equals w. The implementation of display uses self.0 to access the inner vec_t because wrapper is a tuple struct and vec_t is the item at index 0 in the tuple. Then we can use the functionality of the display type on the wrapper. The downside of using this technique is that wrapper is a new type, so it doesn't have the methods of the value it's holding. We would have to implement all the methods of vec_t directly on wrapper, such that the methods delegate to self_0, which would allow us to treat wrapper exactly like a vec_t. If we wanted the new type to have every method the inner type has, implementing the deref trait, discussed in chapter 15 in the treating smart pointers like regular references with the deref trait section on the wrapper to return the inner type would be a solution. If we don't want the wrapper type to have all the methods of the inner type, for example, to restrict the wrapper type's behavior, we would have to implement just the methods we do want manually. Now you know how the new types pattern is used in relation to traits. It's also a useful pattern even when traits are not involved. Let's switch focus and look at some advanced ways to interact with Rust's type system. And so that is advanced traits. So we're moving on to advanced types. Advanced types. The Rust type system has some features that we've mentioned in this book but haven't yet discussed. We'll start by discussing new types in general as we examine why new types are useful as types. Then we'll move on to type aliases, a feature similar to new types but with slightly different semantics. We'll also discuss the bang type and dynamically sized types. Note, the next section assumes you read the earlier section, the new type pattern to implement external traits and external types. All right, let's dive in. Let's begin. Using the new type pattern for type safety and abstraction. The new type pattern is useful for tasks beyond those we've discussed so far, including statically enforcing that values are never confused and indicating the units of value. You saw an example of using new types to indicate units in listing 1923. Recall that the millimeters and meters structs wrapped U32 values in a new type. If we wrote a function with a parameter of type millimeters, we couldn't compile a program that accidentally tried to call the function with a value of type meters, or a plain U32. Another use of the new type pattern is in abstracting away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type if we use the new type directly to restrict available functionality, for example. New types can also hide internal implementation. For example, we could provide a people type to wrap a hash map I32 in string that stores a person's ID associated with their name. Code using people would only interact with the public API we provide, such as a method to add a name string to the people collection. That code wouldn't need to know that we assigned an I32 ID to names internally. The new type pattern is a lightweight way to achieve encapsulation to hide implementation details, which we discussed in the encapsulation that hides implementation details section in chapter 17. Creating type synonyms with type aliases. Along with a new type pattern, Rust provides the ability to declare a type alias to give an existing type another name. For this, we use the type keyword. For example, we can create the alias kilometers to I32, like so. Type kilometers equals I32. Now the alias kilometers is a synonym for I32. Interesting. Okay. So even though we created this type kilometers, it's now just like it's going to be treated like an I32. Unlike the millimeters and meters types we created in listing 1923, kilometers is not a separate new type. Values that have the type kilometers will be treated the same as values of type I32. So type kilometers equals I32. Let x I32 equals 5. Let y kilometers equals 5. And we can actually then add them together because they're the same type. Because kilometers and I32 are the same type, we can add values of both types, and we can pass kilometer values to functions that take I32 parameters. However, using this method, we don't get the type checking benefits we get from the new type pattern discussed earlier. The main use case for type synonyms is to reduce repetition. For example, we might have a lengthy type like this. So box, fn plus send plus static. Writing this lengthy type in function signatures and as type annotations all over the code can be tiresome and error prone. Imagine having a project full of code like that in listing 1932. So yeah, that sucks, having this all over the place. A type alias makes this code more manageable by reducing the repetition. In listing 1933, we've introduced an alias named thunk for the verbose type and can replace all uses of the type with shorter alias thunk. Type thunk equals box, sign function plus send plus static. Let f of type thunk equals box new, and then it's basically just the new is going to hold this this closure. Function takes a long type, so it takes a thunk, returns a long type, and it returns a thunk. This code is much easier to read and write. Choosing a meaningful name for a type alias can help communicate your intent as well. Thunk is a word for code to be evaluated at a later time, so it's an appropriate name for a closure that gets stored. Type aliases are also commonly used with the result TE type for reducing repetition. Consider the standard IO module in the standard library. IO operations often return result TE to handle situations when operations fail to work. This library has a standard IO error struct that represents all possible IO errors. Many of the functions in standard IO will be returning result TE, where the E is standard IO error, such as these functions in the write trait. So standard IO error, standard format, public trait write. So function write, this takes a mutable reference to self, takes in a buffer, which is a vector slice of U8, returns a standard result. The result, I don't actually have this near, so the result error is repeated a lot, as in like this thing, right? As such, standard IO has this type of alias decoration. Type result T equals result T, standard IO error. Because this declaration is in the standard IO module, we can use the fully qualified alias standard IO result T, that is a result TE with the E filled in as standard IO error. The write trait function signatures end up looking like this. Interesting, so you don't need to put the error in because it's being automatically done for us. I don't know how much actually. Well, I guess because these are just the function declarations in the trait. Like they're not the implementation details, which still need to be done. The type alias helps in two ways. It makes code easier to write, and it gives us a consistent interface across all of standard IO. Because it's an alias, it's just another result TE, which means we can use any methods that work on result TE with it, as well as special syntax like the question mark operator. The never type that never returns. Rust has a special type named bang that's known in type theory lingo as the empty type because it has no values. We prefer to call it the never type because it stands in the place of the return type when a function will never return. Here's an example. So function bar returns nothing. This code is read as the function bar returns never. Functions that return never are called diverging functions. We can't create functions of the type bang, so bar can never possibly return. But what use is a type that can never create values for? Recall the code in listing 2.5. We've reproduced part of it here in listing 1934. So let guess, U32, match guess trim parse. Okay. At the time, we skipped over some details in this code. In chapter 6, the match control flow operator section, we discussed that match arms must all return the same type. So, for example, the following code doesn't work. So, OK5, there, hello. Because they need to be the same type. The type of guess in this code would have to be an integer and a string. And Rust requires that guess only have one type. So what does continue return? How are we allowed to return a U32 from one arm and have another arm that ends with continue in listing 1934? As you might have guessed, continue has a bang value. That is, when Rust computes the type of guess, it looks at both match arms, the former with a value of U32 and the latter with bang value. Because bang can never have a value, Rust decides that the type of guess is U32. Okay. The formal way of describing this behavior is that expressions of type bang can be coerced into any other type. Oh, really? So bang can be any type, essentially. We're allowed to end this match arm with continue because continue doesn't return a value. Instead, it moves control back to the top of the loop. So in the error case, we never assign a value to guess. The never type is useful with a panic macro as well. Remember the unwrap function that we call on option T values to produce a value or panic. Here's its definition. So implement T option T. Public function unwrap self returns a T, match self, and then it just panics when it's not that one. In this code, the same thing happens as in the match in listing 1934. Rust sees that val has the type T and panic has the type bang. So the result of the overall match expression is T. This code works because panic doesn't produce a value. It ends the program. In the none case, we won't be returning a value from the unwrap. This code is valid. One final expression that has type bang is a loop. So a loop returns a bang too. Here the loop never ends, so bang is the value of the expression. However, this wouldn't be true if we included a break, because the loop would terminate when it got to the break. Dynamically sized types and the sized trait. Due to Rust's need to know certain details, such as how much space to allocate for a value of a particular type, there's a corner of its type system that can be confusing. The concept of dynamically sized types sometimes refers to as DSTs or unsized types. These types let us write code using values whose size we can know only at runtime. Let's dig into the details of a dynamically sized type called stir, which we've been using throughout the book. That's right, not reference to stir, but stir on its own is a DST. We can't know how long the string is until runtime, meaning we can't create a variable of type stir, nor can we take an argument of type stir. Consider the following code, which does not work. So that S1 type stir equals hello there. That S2 of type stir equals how's it going? Rust needs to know how much memory to allocate for any value of any particular type, and all values of a type must use the same amount of memory. If Rust allowed us to write this code, these two stir values would need to take up the same amount of space. Why is that? Because they're just specific types, but they're in different variables. But they have different lengths. S1 needs 12 bytes of storage, and S2 needs 15. That's why it's not possible to create a variable holding a dynamically sized type. This one feels a little bit odd. I want to try this out. Let's see. Rust. There's like a sandbox play with thing. Playground. That's what. It remembers the last thing I was doing. Okay, I don't need you. Just put you in here. The expected stir found reference. Oh, because this is a reference here. Found a static string. The trait bound stir standard market size is not satisfied. All local variables must have a statically known size. Okay, so we would need to annotate and tell it how big it was. Interesting. Rust needs to know how much memory to allocate for any value of a particular type, and all values of a type must use the same amount of memory. Okay, so what do we do? In this case, you already know the answer. We make the types of S1 and S2 a reference to stir rather than a stir. Recall that in string slices section of chapter 4, we said the slice data structure stores the starting position and the length of the slice. So although a reference to T is a single value that stores the memory address of where the T is located, a reference to stir is two values, the address of the string and its length. As such, we can know the size of a string slice value at compile time. It's twice the length of a U size. That is, we always know the size of a string slice, no matter how long the string it refers to is. In general, this is the way in which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. The golden rule of dynamically sized types is that we must always put values of dynamically sized types behind a pointer of some kind. We can combine stir with all kinds of pointers. For example, box stir or RC stir. In fact, you've seen this before, but with a different dynamically sized type, traits. Every trait is a dynamically sized type we can refer to by using the name of the trait. In Chapter 17, in the Using Trait Objects that allow for values of different types section, we mentioned that to use traits as trait objects, we must put them behind a pointer, such as a reference to dyn trait or box dyn trait. RC dyn trait would work too. To work with DSTs, Rust has a particular trait called the sized trait to determine whether or not a type's size is known at compile time. The trait is automatically implemented for everything whose size is known as compile time. In addition, Rust implicitly adds a bound unsized every generic function, that is, a generic function defined like this. So function generic t is actually treated as though we'd written this. Function generic t sized. Interesting. By default, generic functions will only work on times that have a known size at compile time. However, you can use the following special syntax to relax this restriction. Function generic t size, question sized. Interesting. A trait bound on question mark sized is the opposite of the trait bound on sized. We would read this as t may or may not be sized. This syntax is only available for sized, not for any other traits. Also note that we switched the type of the t parameter from t to reference to t. Because type might not be sized, we need to use it behind some kind of pointer. In this case, we've chosen a reference. Next, we'll talk about functions, closures. Oh, this isn't too long. And this is going to be the last section of this. I'm going to go a little bit long just so we can finish this out. We can start the project tomorrow. Advanced functions and closures. Finally, we'll explore some advanced features related to functions and closures, which include function pointers and returning closures. Function pointers. We've talked about how to pass closures to functions. You can also pass regular functions to functions. This technique is useful when you want to pass a function you've already defined rather than defining a new closure. Doing this with function pointers will allow you to use functions as arguments to other functions. Functions coerce to the type fn with a lowercase f, not to be confused with the fn closure trait. The fn type is called a function pointer. The syntax for specifying that a parameter is a function pointer is similar to that of closures, as shown in listing 1935. So, f is type fn i32. Is that fn that takes i32 or an fn that returns i32? Interesting. This code prints the answer. The answer is 12. We specify that the parameter f in the do twice is an fn that takes one parameter of type i32 and returns an i32. We can then call f in a body of do twice in main. We can pass the function named add1 as the first argument to do twice. Unlike closures, fn is a type rather than a trait, so we specify fn as the parameter type directly rather than declaring a generic type parameter with one of the fn traits as a bound trait. Function pointers implement all three of the closure traits, fn, fn mute, and fn once. So you can always pass a function pointer as an argument for a function that expects a closure. It's best to write functions using a generic type and one of the closure traits so your functions can accept either functions or closures. It's best to write functions using a generic type and one of the closure traits. Okay. An example of where you'd want to only accept fn and not closures is when interfacing with external code that doesn't have closures. C functions can accept functions as arguments, but C doesn't have closures. As an example, interesting, so functions can be arguments, but C doesn't have closures. As an example of where you could use either a closure defined inline or a named function, let's look at a use of map. Use the map function to turn a vector of numbers into a vector of strings. We could use a closure. This. So list numbers, list strings, iter.map, and then our closure. Or we could have a named function as an argument to map instead of doing a closure. So map TwoString string. So it's just going to run that function. Note that we must use the fully qualified syntax that we talked about earlier in the advanced trait section because there are multiple functions available named TwoString. Here we're using the TwoString function defined in the TwoString trait, which the standard library has implemented for any type that implements display. Some people prefer this style, and some people prefer to use closures. They end up compiling to the same code, so use whichever style is clearer to you. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases, where you might want to return a trait, you can instead use the concrete type that implements the trait as the return value of the function. But you can't do that with closures because they don't have a concrete type that is returnable. You're not allowed to use the function pointer fn as a return type, for example. The following code tries to return a closure directly, but it won't compile. Returns closure. It's trying to return this, but you're trying to return I32. This is returning a closure. The error references the size trait again. Rust doesn't know how much space it will need to store the closure. We saw a solution to this problem earlier. We can use a trait object. So we can just return a box and just wrap the closure in a box. This code will compile just fine. For more about trait objects, refer to the Using Trait Objects that allow for values of different types section in chapter 17. Could we have just done, I almost wonder, could we in here create this function and we're going to call it, so I guess we're going to call let my closure equals returns closure and just absolutely nothing here. If we do this, it's going to error out, right? Yeah, so size is not. Can we just say this is an fn? Oh, so we can't just say like it's returning type fn. Okay, so that then makes more sense. The error references the size trait again. Okay, so we just wrap it in a box. Summary. Water. Woo, now you have some features of Rust in your toolbox that you won't use often, but you'll know they're available in a very particular circumstances. We've introduced several complex topics so that when you encounter them in error message suggestions, or in other people's code, you'll be able to recognize these concepts and syntax. Use this chapter as a reference to guide you to solutions. Next, we'll put everything we've discussed throughout the book into practice do one more project. So we're coming to the end. Final project, building a multi-threaded web server. That's going to be super fun to sort of go through this. I know it's going to be multiple 3 parts in here, but that's fine. And we probably won't go through the appendix. We might like take a very quick look at it, but for the most part, then we'll just start building our own projects. But let's go ahead and update where we're at. So first of all, we added something to fix. Added a fix we found. And also in the README, where we're currently at, is now final project, building a multi-thread web server. Save you and update where you're at too. On to the project. And I'll send that on up. All right, so that's up there on GitHub. I've got links to that in case anybody wants to see those. It is about 8 o'clock. I was able to finish on time today. So tomorrow morning at 7 a.m. Mountain Time, I'm planning on beginning that project, and then we'll just see how long that takes. We might be able to finish it this week, and then that will be the end of this epic journey that we've been on of going through the Rust book. Then we'll begin to actually program, well, real stuff. Anyways, thank you everybody for watching, and I'll see you tomorrow.